Welcome to Empowered Learning. This video will be about the integral test. And what the integral test is another tool that we use to be able to tell whether a series is convergent or not. And we normally use this tool whenever the nth term test for divergence doesn't work, or if we don't recognize that the series that we're dealing with is either a geometric series, a harmonic series, or a telescoping series. And so we know in the case of the series not being geometric or harmonic, normally what we want to do is look at the sequence of partial sums, which we denote as S sub n. And so that's what we see here. And we want to take the limit of that to see if that limit exists. And of course, if it does, then we know that the corresponding series that we're talking about is going to be convergent. So what the integral test does is it gives us a way to be able to figure this out by basically using improper integrals. Okay. And specifically what we want to accomplish here is to find out how to tell whether a series is convergent or divergent without having to do this whole thing of figuring out what is going to be the sequence of partial sums from the sequence that the series originated from. We don't want to do that. And for this particular series that are convergent, we want to be able to find an upper and lower limit or bound for it. So those are the two things that the integral test is good for. So to satisfy our first objective, which is we just need to be able to use the integral test to figure out whether a series converges or not as well, we're going to go ahead and address that first by stating what the integral test is and doing some examples on that. And so we're also going to give some insights into what the test actually says, because there's, of course, a lot of wording in this test. It's really a theorem, but we're going to call it a test because it's a procedural theorem. And I'm going to just kind of break out what some of the actual phrases mean so that we have a full understanding of what are the requirements that we have to meet in order for us to use this particular test. Okay. So let's start off here by just reading what the integral test actually says. So suppose that we have some function f that is continuous. So that's one important thing, that it is positive. And of course, what that means is that for all the x values that we're going to be considering, its y values are going to be greater than 0. And we want f also to be ultimately decreasing. Okay. And what that means is that as the values of n for the sequence, for the values of x for this particular function, f of x is, because we're saying f here, but it implies that we're talking about f of x. So for a function f of x, as x approaches infinity, what we want to happen is that the y values of our function f of x start to get lower and lower. Okay. Now, what we mean by lower and lower is that eventually it's going to decrease. Now, of course, we would like it to go to 0, but that doesn't necessarily mean if the function is not going or converging to 0 as x gets larger and larger, that doesn't necessarily mean that it's not ultimately decreasing. Okay, because we can have a situation where our function has a horizontal asymptote, and it's, let's say, decreasing to some horizontal asymptote y equals 2. We could have that, but of course, as long as the function itself is ultimately, its y value is ultimately getting lower and lower and lower as x gets larger and larger and larger, that's all that matters. Okay, so if we have all those conditions and we're considering this on the x value interval from 1 to infinity, and we're specifically picking 1 to start because we're really trying to parallel f of x to corresponding sequence, which would be a function of n. Okay, And of course, our natural numbers start at 1. And thus, if we're trying to do an analog of this sequence to model this, of course, having x be at 1 would be the lowest value that x could possibly have. Okay, so I'm going through all that to say that's what this first sentence is trying to set up. The fact that we want a function that is continuous, that all its y values are positive, and that as x goes to positive infinity, the y values for the function f of x are going to get lower and lower and lower. Okay, and again, that doesn't mean to 0 or to negative infinity. It just means lower than the previous value. Okay, so we have all that in place, and we consider that our sequence from which the series that we're going to be talking about here originates from is a function of n. Then we say that this particular series here is convergent if and only if the improper integral is convergent, meaning that when we evaluate the improper integral, we're going to get a real number for an answer. Okay. Now, specifically speaking here, for the integral test, we know that if the improper integral of the function that is sort of the analog for the sequence that we're talking about, if it is convergent, then the corresponding series is convergent. If the improper integral for the analog function that's supposed to mimic what's happening with the sequence is divergent, then that means that the corresponding series will be divergent as well. Okay, and that's basically what the integral test is. So what I'm going to do now is just sort of elaborate on some of the concepts that I was talking about here in this first sentence to kind of give you a visual of what that's talking about. So from our first note, we see here that ultimately decreasing means that, again, as x approaches infinity, my y values will continue to get lower and lower and lower. Now, in this example, please note that the example that I've drawn here is a case where as x is approaching infinity, f of x is approaching 0. Okay, but that's not always true. I can have a case where as x approaches infinity here, this could just be, like I said before, 2 if, let's say here we had a horizontal asymptote, and let's say this horizontal asymptote was at y equals 2. So that's very possible too. The main thing here is that we see how our function starts off decreasing, then it increases, then it decreases again, then it increases. But ultimately, as x approaches infinity, it starts to decrease again. Okay, and that's what that ultimately decreasing phrase means in the integral test. So the second note that we want to illuminate here is that we do not always have to start with n equals 1. Okay, and that kind of goes back to this particular interval here. So that half open interval there, the reason why it's stated because it's the largest one that can be considered. Okay, but we can start at 2, we can start at 3, we can start at 4, we can start at 10. All of that is okay. But we know that we can't consider an interval any larger than from 1 to infinity, where 1 is included going all the way to infinity. Okay. So in the example that I have here, we see that we have this particular series, and it starts at n equals 4. Okay, and we could use this particular improper integral to be able to evaluate it to see, hey, is it going to converge or not? Okay. Now, note that if we find that this particular series is convergent by finding that this particular improper integral is convergent, then it'll also be true by default that the series which is the same as this one, but it starts at 1 for n instead of 4, will also be convergent because of the fact that this particular series, when it starts at 1, is just these 3 numbers added on to what this series already is. Okay, And let's say this equals to some value s, where we're just going to have s plus 3 other real numbers, and the sum of those plus whatever s is will be the new real number that this particular series will converge to. Okay, so that is the second thing that we want to note. So again, although this says from 1 to infinity, we can consider 2 to infinity, 3 to infinity, 4 to infinity, so on and so forth. All right, so let's keep going here. Now, and I'm not going to go deep into this, but the integral test here, if we really look at it, is just a very specific case of the direct comparison test for improper integrals. Okay, and you can kind of see with the conditions that the integral test has and the conditions for the direct comparison test for improper integrals has, you're going to see that they kind of mimic each other, but the integral test has a few more conditions with it. Okay, and again, I'm not going to go into detail with that because that's not terribly important for what we need to talk about here. But if you're interested, you can go back and watch my videos on improper integrals and compare what the direct comparison test for improper integrals is to what the integral test is, and you'll see how the integral test is like the direct comparison test, but it has a few more conditions that kind of rein you in a little bit. Okay, so it makes it more restrictive on what your function f of x has to look like. All right, so our objective one was just to be able to use the integral test to be able to figure out whether a series converges or not. Objective number two, if you remember, was about being able to establish a lower and upper bound for a particular series. Okay, and so the remainder estimate test is the actual procedural theorem that allows us to be able to get that estimate. And so I'm going to quickly talk about that here. So the remainder estimate test basically says if we are considering some function f of k, which is going to be a sub k. So we're basically saying that this a sub k is a sequence, and we know that it is a function of k, and we're assuming that k is some natural number here. Okay, so that's the first thing. The second thing is, of course, if we're looking at f as a continuous positive, and this says decreasing, but it should be ultimately decreasing function for values of x that are greater than or equal to n, then what this is saying here is that in addition to looking at a sequence, that its behavior can be modeled by, a sequence, first of all, that is going to be a function of k. We're also saying here that f is actually f of x, which is the continuous time analog, or the function where we can have more than just natural numbers be in the domain, is going to mimic the behavior of this particular sequence as well. If we have all that, and we know that we have a function that is continuous, positive, and I should put ultimately decreasing for all values of x greater than some natural number where we'll start at, and we'll have all this, and we know that our series is also convergent. So to put this all into perspective here, we actually got three separate things going on. We're able to look at our sequence from which our series comes from as a function of a natural number. We also can look at the corresponding function in the continuous world, if I could call it that. And this function has to be continuous, positive, and ultimately decreasing. And on top of that, we have to know that this particular series that we've been considering in the first place is convergent. So we got all three of those things going on. If we have all three of those things going on, then we can say that our remainder estimate, meaning what is going to be our value for the sum of the series, if we were to list the first n values of that series, well, it will be just whatever the actual sum is if we were allowed to go, if n was allowed to go to infinity, minus what the nth partial sum of that particular sequence would be. So we subtracted that from the actual value. And so that essentially would be the remainder, okay? Because of course, if we had a list of values, we would have s of n plus 1, and then we'll just keep on going until we get to theoretically what s of infinity is. And of course, this portion here with the sequence of partial sums, what this is actually the s part here, okay? And what remains, what this s of n here is like the difference in between that, what this is actually just all those numbers. And I'll just go ahead and list them out. So we'll have a of n plus 1 plus a of n plus 2. And we just keep on going. So that's what the remainder is there. Technically, that's what it is. So what we're saying here is that instead of us having to go through all this stuff that I said here to try to figure out what the remainder will be, all we have to do is evaluate the improper integral of our analog function to the sequence from n to infinity, and that will be the upper limit, and then the lower limit will be the same improper integral, but our limit of integration now is n plus 1. And so this graph here is just basically saying that the area under the curve for a sub 2, of course, is going to be smaller than the area under the curve of the total here. And of course, the difference in between what the total area under the curve is, which is from here on to infinity, and what this is to infinity, which is this part here, would actually give us an idea of what the remainder would be from our summing this particular series up if we can only go to the first n terms, okay? So that is essentially what that particular test or theorem is talking about. Now, one important, useful piece of info that we need to know and have it in our back pocket here is we need to be able to recognize what is a P series, okay? Now, if you go back to the improper interval video that I talked about, we had some improper integrals that looked like this, okay? And we said that this particular improper integral here will converge as long as P is greater than 1. If P was less than or equal to 1, then this particular improper integral would diverge, okay? So converge if P is greater than 1, it will diverge if P is less than or equal to 1, okay? And so because of that, one of the things that we have to remember here is that this integral sign is actually what this means here. So whenever we take the infinite sum of something, an integral sign actually means infinite sum. And that's one of the reasons why this whole integral test thing works, is because whenever we're trying to sum, trying to do a series here, what we're actually saying when n goes from some value to infinity, that we're essentially doing an infinite sum, okay? And so again, the point here is that if we recognize that we have a series that is of this profile here, of this format, then we can automatically call it a P series. And depending upon what P is, we can determine whether that series is convergent or not. And we don't have to go through the whole ordeal of actually evaluating an improper integral. Okay, so that's why that's important. Now, of course, going back to the remainder estimate test here, we're just doing a little fancy footwork here, that if we define our remainder for the first in terms, or how much we're going to be off from the actual sum of whatever series that we're talking about, is going to be defined this way. Then, of course, we know here that if we do this particular estimate here plus S of n, then, of course, we could add S of n here. This is already going to be what the max value of it could be in the first place. So my point here is that if we have these two together, this is essentially what the sum actually is, because this is how much we've calculated already. This is what remains, okay? And so, of course, that would be the actual sum. And here, we just kind of take what we had here and here and bring it down. So what we see here is that if we do the nth partial sum, whatever that value is, plus this improper integral, that is going to be a lower bound. And of course, whatever this is going to be the upper bound for it. And in ideal case, the left-hand side and the right-hand side would be the same thing. So it'll sandwich it in. And of course, everything will just go to whatever the sum actually is. Okay, so what we're going to do now is just do some examples so that we can kind of get our footing under how we can actually use the integral test. So to use the integral test, remember that there are three conditions that our function or sequence is going to have to meet. Okay, so first, and I'll just kind of put a star by this one because this is not really a part of the list, but we need to be considering this. So the first thing is that we need to be able to say that our sequence can be modeled as a function of n, where n is natural number. And I'm going to do this symbol here to say that the way that it acts is going to be equivalent to some function f of x. Okay. Now, first thing that we need to make sure is that f of x is continuous on the interval that we're considering. And in this case, since we're starting at n equals 6, this needs to be continuous on the interval from 6 to infinity, including 6. So that's the first thing. The second thing is that f of x needs to be positive on this particular interval as well. So that means all of my y values for my function f of x is going to have to be something that is greater than 0. And then the last thing here is that f of x has to be ultimately decreasing. Okay. Now, there's two ways we can actually test to see whether that's going to happen. The most traditional way of doing it would be to figure out for what values of x is the first derivative of our function negative. Okay. And specifically in this case, if we find that the first derivative of our function for any x value in this interval from 6 to infinity is negative, then of course that would be the ideal case for our function to be ultimately decreasing. Okay. All we really care about is if we take the first derivative of this function at some point as x approaches infinity, is it going to be negative? And so by finding this particular, the answer to this particular inequality here, if we have some portion of our interval from 6 to infinity where a portion of it is some other x value on to infinity, then we know that yes, it ultimately decreases. Okay. So to kind of contrast that, let's say we had a situation where f of x was greater than 0 for, let's say, 100 to infinity. Let's say we had that, but f of x, the derivative of f of x was write this here, was negative only for values from, let's say, 6 to 100 like this. Okay. So if we had that, then our function f of x would not be ultimately decreasing. So therefore, we wouldn't be able to use the integral test to be able to evaluate, or to be able to determine whether this particular series here would be convergent or not. So that's what we mean by using the derivative here to ultimately to find out whether our function is ultimately decreasing, and what I mean by saying, hey, we need to find out when the first derivative of our function is going to be negative. Okay. All right, so I'm going to erase this, and then we're going to talk about the other way we could figure that out as well. Now, the other way that we could figure out whether our function f is ultimately decreasing, if we had a situation where our function f of x could be composed of, let's say, a function a of x divided by b of x, and if the limit as x approaches infinity of a of x over b of x here equals 0, then that's another way of us knowing that our function is going to be ultimately decreasing. Okay. Essentially, what we're saying here is that as x approaches infinity here, my function a of x is going to be smaller than b of x. Okay. So basically, b of x is a function that grows faster than f of x. Or you can say that your ratio of two functions, that function will be bottom heavy. Okay. And of course, we use that in pre-cal terms, but in general, this is whenever we take the limit of a function divided by another, that's one of the ways that we can figure out which one grows faster than the other. Okay. And if we get 0, then we know that the bottom function grows faster than that. If we get, let's say, infinity, then we know that the function in the numerator grows faster. And if we get some number like 2 or 5 or 15, then we say that both these functions, a of x and b of x, grow at the same rate. Okay. So they grow relatively at the same rate, even though one may be a little bit bigger than the other. All right. So now that we know what it is that we're looking for, we're going to quickly look at this example here and make sure that we are convinced that all three of these things are satisfied. Okay. So for starters, is the corresponding function for this. So let's say the corresponding function for this will just be 2 divided by 5x plus 6. So is this function continuous on the interval from 6 to infinity? Well, the answer to that is yes, because we know that the only place where a rational function will not be continuous is where its denominator is going to be 0. And of course, if I set 5x plus 6 to be equal to 0, I would get that x is negative 6/5, and that is the only x value to where this function is going to not be continuous at. And of course, negative 6/5 is not in this interval here, so we're good with this one. Okay. Next, is my function positive, or the y values of my function positive for values of x 6 and higher? Okay. So for that one, the answer to that would be yes as well. And we can easily see this because, of course, my numerator, which is 2, is always a positive number. And if I plug in any value that is 6 or higher in the denominator, that's always going to be a positive number as well. And so a positive divided by a positive is a positive. So, of course, that checks that box as well. Now, does this function ultimately decrease? Okay. Well, one of the simple ways that we could look at this is I could look at this function f of x as a function, a constant function being divided by a linear function. Okay. So if I look at it that way, I know that my linear function is going to grow faster than my constant function. So just by that common sense way of looking at it, I know that this particular function is going to be ultimately decreasing as x approaches infinity. Okay. Now, Another way that I could do it is I could evaluate the limit as x approaches infinity of this particular function here. And of course, if I plug in infinity for x, I know that eventually I'm just going to have 2 divided by infinity, which goes to 0. So, of course, whenever we get 0, like I said over here before, your bottom function is the one that grows faster. And thus, we know that this function is going to ultimately decrease. Okay. Now, the most complicated way to do this is to find the first derivative and then figure out for what values of x is the first derivative going to 0. I'm not going to do that because, again, we've already shown in 2 other common sense ways that this particular function here, 2 divided by 5x plus 6, is going to be ultimately decreasing. Okay, so we have this box checked, and we know that now that we can use the integral test. So I'm going to go ahead and erase all this, and then we're actually just going to apply the integral test. Okay, so now that we know that our function is continuous, it is positive, and it's ultimately decreasing on this interval from 6 to infinity here, we now know that if we evaluate the improper integral that I'm writing here, we evaluate this improper integral and it converges, then that means that this corresponding series will converge as well. Okay. So with that being said, all we need to do now is just evaluate this improper integral. So to do that, we could start off by essentially, let's just go ahead and do the substitution rule here. Okay. So if we do the substitution rule, let's let u equal 5x plus 6, which means that du is just going to be 5 times dx. Okay, so we can look at it that way. And so from that, we could just say that du divided by 5 is going to be dx. Okay, so we have a way of replacing dx in terms of u, and we can also replace 5x in terms of u. I'll go ahead and also do this as well. We'll say that u of 6, this is going to be 5 times 6 plus 6, which is 36. And we know that u of infinity still is going to be infinity. Okay. So I'm doing that so we could change our limits of integration in terms of u instead of having in terms of x, so I don't have to go back and back substitute. So once we have that, then this will be going from 36 to infinity, and we'll have 2 times 1/5 du, all that over u. Okay. All right, so with that being said here, all we have to do now is evaluate this. And of course, the proper way to do this is that we're going to say the limit as b approaches infinity. And let me switch this up here. Not b, because our variable is in u. So as u approaches b, and we're going to say it's approaching it from the left of, and then here we're going to do the integral from 36 to b, 2/5 du over u. Okay. And so from here, again, we just have limit as u approaches b from the left. If we were to take the antiderivative of this, this is just going to be 2/5. And the antiderivative of 1 over u du is just going to be natural log of absolute value of u. Since the values of our limits of integration are all positive and greater than 1, then we don't have to worry about the absolute value sign. So we're just going to say that this is natural log of u, and that's going to get evaluated from 36 to b. And so, of course, from here, we could factor out the 2/5, and we'll just basically have 2/5 limit as as u approaches b there. And of course, all this is going to be approaching infinity as well. Yeah, and so that reminds me here that I should probably write this way. So as b approaches infinity, yeah. So that's probably a better way to do it, because once I'm done with all of this, I know that it's going to be approaching infinity anyway. So that's a better way to write that. So let's change that here. Yep. Yeah, if I was approaching like some number and I had a vertical asymptote, then the notation that I used earlier would probably make sense. But since we're just going to, infinity, then I can just use this notation that I'm talking about here. Yeah. I'm trying to get this thing to look right, and it's not working for me. Okay, all right. So here, this will be as b approaches infinity, and if I go ahead and substitute this in, this will be natural log of b minus natural log of 36. Okay, and so from at this point, you'll see here that this is not natural log of 6, by the way. It's natural log of b. And so b would be basically approaching infinity. So if I was to execute what I'm talking about here, this would be 2/5, and natural log of infinity would be infinity minus natural log of 36. And of course, when we look at that, since that's going to infinity, all of this will just be infinity. And therefore, we know that this particular integral, improper integral, will diverge. And since it's diverging, then it means that this corresponding series will also diverge because of that. All right, so if we look at this second example here, we're asked to use the integral test to be able to prove whether this series converges or not. But if we look closely at this one, we'll actually see that this is a geometric series, and I'll show you why that is. So if we just consider what we have in here to be some sequence a sub n, then here we could rewrite what we have. I'm just going to write it this way. We could rewrite this as a negative and then 1 raised to the n over 4 raised to the n. And of course, since both of these, the 1 and the 4, are both raised to the n, I could rewrite this way. And thus, the negative hanging out there could be understood as a -1. I could rewrite that like this. And one more step, I could actually do this as well. Let's try to get those 4s looking a little better here. Sometimes the 4s work out for me and sometimes they don't. And as you see right now, they are not. All right, so let's try it that way. All right, so we could rewrite it this way. Now, of course, that means here that this -1 times the 1/4 could just be rewritten like this. And again, I kind of took the scenic route to do this to kind of make my point that this will actually fit the profile of a times r raised to the n minus 1. And if you don't recognize what that is actually the function part of a geometric series. So here we note that if we do summation from n to 1 to infinity of a times r raised to the n minus 1, this is a geometric series where its sum we know is always a divided by 1 minus r, where a is considered to be the first term in the geometric series, r is the common ratio. So we see what we have here can be expressed that way, where a is equal to 1, a is equal to a negative 1/4 rather, and r is equal to a positive 1/4. And so from that, we know that since r is in between negative 1 and 1, because the geometric series, it converges when our value of r is in between negative 1 and 1. Okay, and so since this is the case, we know that this particular series converges here. Now, we could also show that this particular series will converge by doing the integral test as well. Okay, and if we did that, essentially what we would have to do is take the integral from 1 to infinity of essentially negative 4 raised to the negative x dx here. Okay, and I'll do this quickly to kind of show you that it works both ways here. So if we did this, and this will be a negative right here as well, because we're taking this and we're putting it in the numerator. So one thing that I can do here is I could use substitution. And if I use substitution, then u would be equal to a negative x, which means that du would be equal to negative dx, or negative du is equal to positive dx. And also here, u of 1 would also be equal to, if we plugged in that negative 1, and u of infinity here would also be negative infinity. So if we looked at everything here, we had this negative out, u of 1 would be negative 1, u of infinity goes to negative infinity, and now we just have 4 raised to the u du. Okay. And so here we know the limits of integration are out of order. So we would have to multiply times a negative 1 to get them back in order. And that's what this would be here. And then it's just a matter of taking the integral of what we see here. And of course, this would be limit as a approaches negative infinity of this integral here. We have a to negative 1, 4 of u du. And if we worked all that out, the antiderivative of 4 raised to the u, I know this looks kind of bad here, so I'm going to try to make this u look a little different. So 4 raised to the u would just be 4 raised to the u divided by natural log of 4. And that would be evaluated from a to negative 1. And then we would also be doing the limit as a approaches negative infinity for that. And so for here, this would be limit as a approaches negative infinity. Plug in the -1. So this would be 4 raised to the -1 minus, and we'll have 4 raised to the a, and of course all that over natural log of 4. All right, so at this point, we would just plug in a negative infinity here for our a. And here we know that 4 raised to the negative infinity is just like 1 over 4 raised to the positive infinity. This would go to 0. And of course, 4 raised to the -1, that's just the same as 1/4. So what we end up getting is just 1/4 divided by natural log of 4. And even though it is an ugly number, it is a real number, okay? And so because of the fact that this is a real number, that means that this particular improper integral converges, which also means that this particular series converges as well. And so we see in 2 different ways that we prove that this particular series will converge.